All right, so we have a two-stage vapor compression refrigeration cycle. I went through the problem statement and put everything on the diagram there. I've also written out our find and our typical assumptions: steady state, kinetic energy, and potential energy are 0. And so now I'm ready to start solving the problem. So I'm going to start just by figuring out what all the H values are. So H1, we know the quality and we know the temperature. So I just need to look at the saturated tables in English units for ammonia and pull off that H1 value, which is the H sub G value. I also need to get the S value because I'm going to need that to figure out the isentropic H2S, and then use that isentropic efficiency to figure out what H2 is. So there we go. I'm using my isentropic efficiency. I need to figure out what H2S, and that's going to be evaluated at P2, the 80 psi, and S2S, which is equal to S1. So if I look at my tables, I find out that that would be superheated. So my S value, 1.3762, it's going to be between that 1.377 and 1.3585. So I interpolated for 692.14 BTU per pound mass. And then if I plug things in to get H2, I get 707.59. Now I'm ready for H3. I'm given a quality and a pressure. That's enough to go into my saturated tables for ammonia at 80 psi and pull off the H value. I also need to get that S value because I need to use that to find H4S, which is going to be used to find, used with the isentropic efficiency to figure out what that H4 is. So my H4S ends up being 693.53. So if you look in your superheated tables, which I'm not showing here, but if you look in your superheated tables, you will interpolate for 693.53. And then finally plug in and get 705.92 for H4. Now we're ready to go on for H5. So H5, let's see, H5, we're looking at a quality of 0 and a pressure of 250 psi. So here I am on my saturated tables for ammonia, and I get my H sub F value of 167.77. State 6 is really easy because it's an isenthalpic throttling process, or that's what we're going to model it as. State 7, we're given a quality of 0. We also know the pressure is 80 psi. So I go in my saturated tables for ammonia to 80 psi and pull off the H sub F value. And of course, since it's an isenthalpic throttling process, H8 and H7 are equal to one another. So let's see, make sure we got our, well, H7 and H8. There should be an H8 equal to H7 on that little chart there. Okay, so we've got all our H values, even H8, even though it doesn't look like it's there. It's the same as H7. I'm ready to figure out how those mass flow rates are related to one another. So what I'm going to do is I'm going to apply my conservation of energy, my first law, to that direct contact heat exchanger, because that will allow me to relate those M dots, right? There's only one component, and it's that heat exchanger that it relates those mass flow rates. So because all of this is going to be insulated, I don't have any work, I don't have any heat transfer, everything's going to cancel out except the M dot H's. So I've got things coming in at 2 and at 6 and things leaving at 3 and at 7. I also note where my mass flow rates are constant. So 1, 2, 7, and 8, all those M dots are the same. And then 3, 4, 5, and 6, all those M dots are the same. And so all I've done is put those mass flow rates in terms of M dot 1 and M dot 2, since that's what part A is asking me to get. And then I just rearrange, get M dot 3 over M dot 1, solve, and get 1.353. All right, now I'm ready for my power input for the two compressors. So for the power input for the first one, it's M dot 1 times H2 minus H1. Got H2 and H1. The M dot you can find from that 30 tons, the Q dot N, which is 30 tons. You do have some unit conversions, of course. You need to get the tons in terms of BTU per minute, or BTU per minute, and you'll get 11.69. And then plug that in. Once again, watch your units, but you'll eventually solve for 28.38 horsepower. Compressor 2, M dot 3 times H4 minus H3, and you can find M dot 3 from part A, since you also know M dot 1, and you can solve for 30.81 horsepower. And then for your coefficient of performance, it's what you're interested in, and it's a refrigeration cycle, so you're interested in the Q dot N over what you have to put into it, which is the net work input or the net power input, and you've got all of those values, and so it's just plug and chug. Do watch your units, and you get a COP of 2.39. All right, well, I hope that was helpful. Thank you for watching, and let me know if you have questions.